So in the last part, we will discuss on the example, another example that involves the load line. Okay, so we consider the DC load line in the circuit in this figure B3. This is the load line circuit. This is the circuit drawn on the collector characteristic of transistor. So this is IC versus the VCE figure. This figure. So the question is determine the transistor parameter VBE if the established Q point is at the center of the load line. Okay, center at the load line. So you want to determine the VBE. Okay. So how to determine the VBE? Usually, we always assume the VE to be equal 0.7. But now, the question asks us to ignore this assumption 0.7. Instead, we need to calculate the VBE. Okay, we need to calculate the VBE. Okay, so from this load line, we want to have the Q point at the center of the load line. So at the center of the load line is okay, see here, this is the load line. Okay, this is the load line, and this is a cut-off point, and this is a saturation point. Okay, and then you see that one is, this is the IC saturation equal to 8 milliampere, and then this one, the cutoff, equal to VCC. So you know that VCC is equal to 10 volt. So right away you can see that VCC is 10 volt. Okay, and then the middle point is half of the VCC. So at the VCC is equal to 5 volt. So you can see this is the midpoint, where this is our assumption. This is the midpoint. Okay, and then from this one we can get this one. The Q point is IBQ equal to 40 microampere, ICQ is equal to 4 milliampere, and VCEQ equal to 5 volt. Okay, this is our consideration. Okay, so next actually we need to determine the VBE. So how to determine the VBE? Okay, VBE appear at this base emitter loop, KVL. Okay, base emitter loop. So we can do the KVL at emitter loop. Okay. Okay, let me draw this one. We have 6 volt, 33K. We have this one, 6 volt, and then we have this one is this is 33K. Okay, and we have 1K at the emitter. This is the loop one, the loop that you want to analyze. This is the VBE. Okay, and then this one is a base current. Okay, then this one is the emitter current. Okay, the base current is equal to 40 microampere. IC is equal to 4 milliampere. So IE is equal to IB plus IC, which is 4 milli plus 0.04 milli. So we call it 4.04 milli. Okay, we do the KVL. KVL is minus 6 plus IB is 40 microampere, which is 0.04 milli times 33k, and then we have here VBE, and then we have here is IE is 4.04 milli times 1k equal to 0. So you can calculate for every term here. 33 times 0.04, we had 1.32 plus VBE, and then this one is plus 4.04 equal to 0. So VBE is equal to 6 minus 1.32 and then minus 4.04. So you get here is 0.64 volt. So this is the answer for VBE. Okay, the next question is we want to replace or we want to change the configuration. So stated here, the emitter bias in the circuit, the shown circuit require 2 power supply. So see here we have the 2 power supply. So this is VCC at the collector, and we have the VBB at the base. So now we want to instead of 2 power supply, we want to have single power supply. So the single power supply, so we will use the voltage divider circuit. Okay, the question is draw the circuit and determine the RB1 and RB2. Okay, let's draw the current circuit first. So the current circuit first has the VCC, and then we have the RC, we have this emitter, is RE, 1 kilo ohm, and then it has the RB, this is 6 volt, and this is 33 kilo ohm. Okay, so we want to replace with the voltage divider. So how the voltage divider looks like is, instead of having this configuration at the base, so we will have a single supply, and the supply is equal to VCC. So we have say I put the voltage divider circuit. This is 1 kilo ohm, this is RC, this is a VCC. Okay, and then you have 2 resistors here. So this is R1 and R2, and the voltage supply is from the VCC. So this is the voltage divider. Okay, now we want to determine the R1 and R2. So how to determine the R1 and R2? Okay, so you need to do the Thevenin transformation. Okay, you need to do the transformation and establish the same circuit with the current one. Okay, if you compare the current circuit, it has only one power supply. One power supply. Not only we have one power supply directly applied to the base terminal, and we also have one resistor connected to the base. Okay, so this current configuration actually similar to the Thevenin transform. This is Thevenin after the Thevenin transformation. So again, I explain this one. So actually we want to have this voltage divider configuration. We have R1 and R2. But when we do the analysis of R1 and R2, we need to do the Thevenin transformation. When we do the Thevenin transformation, it will go back to the current configuration or current circuit connection. So we can say that the 6 volt here is equal to the V Thevenin. So V Thevenin, our design for R1 and R2 is the design that make the V Thevenin, okay, and with that produce the V Thevenin equal to 6 volt. Okay, and then this is a V Thevenin, and then the R1 and R2 should be the values that make the R Thevenin equal to 33 kilo ohm. This is the R Thevenin. So the R Thevenin is equal to 32 kilo ohm. Okay, what is V Thevenin? V Thevenin, the equation is R2 over R1 plus R2 times VCC. So what is VCC? VCC, although it's not directly provided, VCC we can get the VCC value from the load line. Okay, the VCC value is at the cutoff point, which is 10 volt. So VCC is 10 volt. So times the 10 volt equal to 6. So this is our first equation. So you got this one is R2 equal to 0.6 R1 plus 0.6 R2 and then you got this one okay. Let me do some changing in how we can calculate this one instead of using this approach. Okay, let's see the equation first. You can see another equation for the R Thevenin. Okay, this is the first equation. Okay, another equation from the R Thevenin is R1 times R2 over R1 plus R2 is equal to 33 kilo ohm. Okay, 3 kilo ohm. This is equation number 2. Okay, so from this equation, there's many, as long as you can solve this first and second equation and get the R1, R2, it should be okay. So for now, what I can do is, I can, from the equation 1, I can get this one, R1 plus R2 equal to, so R1 plus R2 equal to 10 over 6 R2. Okay, and then this is, I see this one is 1A equation. So you insert 1A equation to the second equation, you can get this one is R1 R2 equal to 10 R2 6 equal to 33 kilo. So we can cancel out the R2, and then you can get the R1 is equal to, do the calculation here, 33 times 10 and then divide by 6. You have this one, R1 is 55 kilo ohm. So you get the first R1 answer. For the R2, you can use the 1A equation. You can use the 1A equation. So R1 is 51. R1 is 55. Sorry, 55. So you know this one is 55k plus R2 equal to 10 over 6 R2, and lastly you can get R2 is equal to this is 10, 6, 4. Let me calculate this one is R2. This is 55k, and then this is 10 over 6 minus 1. This is equal to 4.6. So this times 6 over 4. 55 times 6 over 4. So you got the answer is 82.5 kilo ohm. So this is your answer. So you have this configuration, the circuit, and you have the value for R1 and you have the value for R2.